Looks like it. Okay, this is the Anova presentation. I think this would be video number 9. And let's get the whiteboard up. It's kind of funny. I always have this ready before I start, but by the time I get the things working, it seems like it goes away. Okay, a little bit about Anova. Uh, Preview of Anova. Um, some of you, most of you have probably seen this, and we're going to certainly give it its a lot of attention because it's going to play an important role. Not the ANOVA that we're looking at here, but the ANOVA tables, and the concept of ANOVA is really important in regression. So anyway, guys, we're going to be talking about analysis of variance. The purpose of this is to compare the population means across K groups. Now, if K is equal to 2, then we're going to run an independent samples t-test. So for the most part, what we're talking here is when the number of groups that we want to compare, the group means, the population means, is when we have 3 or more groups. Okay, now what happens is, let's say we have population number 1, and clearly this population has a population mean. And we have population number 2, which has a population mean. And we have population K, which also has a population mean. Now, you could, this would be kind of a silly study, but let's say someone makes a claim that that IQs are different across political party. I can't even say that without smiling. So if we wanted to, for example, look at IQs across Democrat, Independent, and Republican, and if someone would want to go out and make the claim that IQs differ across political party, what we could do is we could come in and take a random sample of, for example, our first population, second population, third population, implement ANOVA, and address the issue. The last thing you want to do is to, and it seems like it would be applicable here, is to do t-test across groups. In other words, do a t-test to compare Democrat and Independent, do a t-test to compare Independent and Republican, and do a t-test to compare Democrat and Republican. Well, if we did this, we would implement 3 tests. And since each of these tests would more than likely test at 0.05, what we would get into is we would get into a situation where the type 1 error rate, we call that the family-wise error rate, because we would do it, be looking at the error rate across, if you will, family of t-test, would be inflated. So I forget exactly how to calculate that. It would just, I do know that if we have 5 groups, that it seems like the probability of committing a type 1 error is somewhere around 0.3. So it's highly advised not to compare group means by repeating t-test, and it is highly advised to use Anova. So let me get rid of some stuff here. So let's carry out the Anova. So what we would want to do is we want to come in on the first sample and calculate population or a sample mean, sample standard deviation, and get a sample size. We would get a standard deviation, mean, and sample size for the second, and clearly we would get a sample from all of our populations. Now, something that is going to be an issue is something called the grand mean. And guys, the grand mean is just a capital X bar. And this, of course, well, let me back up here. So the grand mean is just going to be if we average add all the samples together, it'll be the mean of all the samples. Now, where I'm really wanting to get here is the next thing, and that's demonstration of what actually happens. The test statistic is the F statistic. And if you remember a little bit about the F statistic when we were looking at distributions the other day, we have 2 degrees of freedom. And we'll call 1 degrees of freedom for the numerator. And we'll call another degrees of freedom for the denominator. It turns out that the F statistic is found by taking the sum of squares for the, let's just call it the between. Okay, hold on, my dog wants out. Okay, so we're going to divide this by the degrees of freedom for the numerator. And the denominator here, we're going to have the sum of squares for what we call within the variation divided by the degrees of freedom for the denominator. So we will have F is the sum of squares between degrees of freedom between divided by the sum of squares within divided by the degrees of freedom within. The numerator turns out to be the mean square between divided by the mean square within. So our test statistic F will follow an F distribution. With 2 degrees of freedom for the numerator and degrees of freedom for the denominator. Now, I should probably tell you a little bit about the degrees of freedom. Let's let K equal the number of groups. Or the number of populations. So we're going to have, population mean 1, population mean 2, up to population mean sub K. The degrees of freedom for the denominator, or I'm sorry, for the numerator, which again we're going to refer to for a while at least as representing the variation between, is nothing more than K minus 1. The degrees of freedom for the denominator, which for the time being we're going to refer to that as the within variation, is n minus k. And guys, n just stands for the total sample size. So n would be I equal 1 to k, the sum of the sample sizes. Well, let's try to make this happen. To give you an illustration, what I mean about the between versus within variation. Now, if we can imagine having different populations, and clearly each one of these, let's just look at a situation where k is equal to 3. So each one of these has clearly a population mean, and the way I've drawn them, clearly the means are different. But we don't know that, and that's why we go out, collect a sample, collect from population number 1, we'll collect sample mean, sample standard deviation, sample size, and do the same for, in this case, all 3 populations. Now, if you can imagine the location of the grand mean, which would be x bar. When we talk about the variation between, we're looking at the variation basically from the centers of the distribution. When we talk about the variation within, we're looking at the variation within the distributions. Now, without getting too crazy here, let's go back again and think about what the F statistic is measuring. Variation between, variation within. Now, Anova has some really strict assumptions. So get this thing to right. Assumptions that must be present in order to implement an Anova. Well, the first thing we need is independence, and you're going to find out in statistics That independence is always a critical issue. Guys, independence at the end of the day just means that the probability of um, uh, of getting one particular measurement doesn't depend on the probability of another measurement in our data set. Another thing that we're going to need is we're going to need normality. And the final thing we need is what we call the HOV. This is homogeneity of variance. In other words, we need an indication that the variance from our first population and the variance of our second population, in this case we're looking specifically at k equal 3, and the variance of our third populations are equal. Now, what if they're not? Well, if they're not, then we're going to get something like this. When we look at our population distributions, then we're going to have one distribution like this, another distribution like this, and possibly another distribution like this. This would be representative of populations which have different variances. But what the F distribution seeks to do, it seeks to control for this value. So again, this value down here, the value in the numerator, looks at the measurement of the variation within the distribution. So if we can get in a situation where we know that our distributions have basically the same shape, same variation, then what happens? Well, now we can concentrate on the variation between the distributions. So if the variation between the distributions controlling for the variation down here in the denominator, well, as the variation between the distributions gets bigger, what happens? Well, our F statistic gets bigger. And guys, as our F statistic get bigger, our p-value gets lower, which is more evidence against our null hypothesis. Speaking of the null hypothesis, let's set this up. The null hypothesis assumes that we have equal population means. The alternative hypothesis is that at least one pair of means differs. So guys, let's carry one of these out, okay? So I want to look at a situation where we have k equal 3 groups. And I found a data set that is going to work fine. What we have, we're actually conducting a completely random design here. And suppose we have 3 new menu items in the 18 restaurants after a week of testing marketing. We want to see if the mean sales volume for the 3 new mean items are all equal. So apparently we have item number 1. And again, what we're measuring here is looks like it's the the sales volume. So item number 1, so 22, 42, and down to 37. And it looks like this data set, we're going to have 6 measures from each population. Item number, and I'm going to show you the status set in entirety once we get into R. So here we got 52, 33, and we have down to 32. And then item number 3, sales volume for it, 16, 24, all the way down to 39. Now what we'll definitely want to do is we'll want to create the standard deviation mean sample size for all of these. And, carry out the procedure. So, guys, let's talk about the procedure. The F distribution, the F statistic can be found by taking the sum from I equal 1 to k of n sub I, each group mean minus the grand mean squared divided by its degrees of freedom. So again, this is going to be our sum of squares between. And I have no idea why that's slanted that way, but it is. The sum squares within is going to, let's see, forget. Okay, it's going to go n sub I minus 1 times the variance divided by n minus k. Now, so guys, clearly we're going to need the sample mean. Sample size is going to be given. It's going to be, I think, 6, 7, I forget. 6, yeah, I think 6 for each. We'll need to calculate the grand mean, and we'll need to obviously get the standard deviation so we can get the variance of each group. So now, ultimately what we want to be able to do here is we want to create an Anova table. And we're going to get into some post hoc analysis too, but for the most part, what we want to do with the Anova table is fill out this table. So we're going to want to look at the between factor, or the between variation, the within variation, and the total variation. So we're going to want to look at the sum of squares. We're going to look at the degrees of freedom. We'll look at the mean square. And that will create the F statistic. And ultimately we'll create the p-value. So let's do that. Now, going to switch things up a little bit here in the way that we do handle our data. I taught a Math 3500 course this past semester, and one of my nightmare presentations was I was trying to look at a factorial design of Anova, and well, it didn't work. I tried handling the data in a way that that didn't work. So I don't want that to happen again. So I've looked around, actually played around with it quite a bit. I think this is going to be the best way for us to handle this. So first thing, let's enter our data, and what I want to do here is I want to get out just to bring up a point, and I want to open up this mass data. I don't know if you guys remember that, but it was part of I think the first presentation. And what I want to do, I want to modify this to, let's call this item 1, item 2, and item 3. That stuff drives me crazy if it's not let's delete these entries. Okay, now let's enter our data. So item number 1, let's see, 242. Always consider having this done before I actually start teaching, but keep forgetting that you guys can stop the stop the recordings and actually enter the data. By the way, worst part of statistics, entering your data. And we got it easy here. We only have 3 variables or 3 populations and 6 scores. So guys, I want to go up here and do a save as. And I'm just going to call this Anova. And save it. And you get all sorts of crazy things, or at least I do. All right. Shut down Excel. I don't want, already saved it. I don't want too much running because with the screen recorder going, with the iPad R going, sometimes things get a little crazy. Now, again, get our working directory. You remember that probably from, or at least I hope you remember that from the first lecture. So we need to set our working directory to users, ddarbro, desktop. Guys, I'm kind of anal about this. I always like to just go back and make sure that that's is my working directory. Now, what I want to do is use data frames. So I can call this Anova. And I want to read CSV. And I think I call this CSV, right? So I get Anova. I have my data. And always check, check for typos, check for different things, especially when your grade's at stake. Although I wouldn't, beat you up too bad if you know what you're doing and just made a typo. Well, everything will be fine. All right, guys. What I want to do next is I want to find some means and standard deviations. So I'm gonna write these things down. So I want the mean of item 1, and I didn't get it. So anybody tell me why? Yep, haven't attached it. So I have to attach. Now I can look at Anova. Now I'll be able to get a mean for item 1. Guys, I'm going to write this stuff down. So 40.33. Standard deviation, item 1, 10.21. Item number 2, 35.83. Standard deviation. $15.72. And for item 3, 25. And standard deviation 9.42. Now, what do you think? We're clearly going to let the procedure, run its course, but I got a mean of 25, mean of 35, mean of 40. I don't know, considering that we've got a standard deviation of 10, 15. Yeah, I don't know. Looks like to me that this mean of 25 will probably be statistically significant with the 40, but it could possibly even be with the 35. But more importantly, at least the way I think about it, is what about our variances? So the variance of item 1, variance of item 2, variance of item 3. Now, I have to admit, I have major concerns whether or not we're violating the homogeneity of variance assumption. But this is not a publication. This is nothing I'm putting my name on. This is just an illustration of Anova to use. So I'm going to go ahead and let it play out. So need the grand mean, guys. We're kind of lucky here in that we have going to go out to 2 or 3 places. We have equal sample sizes. So I can kind of cheat. So the grand mean is 33.722. All right, going to do some calculations here. First thing I want to do is calculate the sum of squares between. So I'm going to call that sum of squares between. And let's think what it is. It's a sum of the sample sizes, which in this case is 6, minus the sum of squares, which would be the difference between the, each group mean and the grand mean. So I'm going to have 6 times 40.33 minus 37.22. I'll tell you what I'm going to do. I'm not going to do it this way. I want to go mean item 1 minus grand mean quantity squared plus, and I'm going to do some copy and paste here. Here I want item 2. You know what? Item 3. Make sense? Okay, let's see what happened. All right, so sum of squares between. So we can find the mean squares between, which is going to be equal to the sum of squares between divided by 3 minus 1. Okay, now sum of squares within. And if you remember, sum of squares within just is our sample size of each group, which in this case minus 1, which will be in this case 5. Don't want to forget this multiplication sign. And going to be multiplied by the variance of item 1 plus 5 times variance of item 2 plus 5 times the variance for item 3. All right. Yes, capitalization. All right, so it's going to work this time. So the mean square within is going to be our sum of squares within divided by its total sample size, which is 24, minus the total groups, which is 23. So guys, our F statistic is going to be mean square between, mean square within, and our p-value will be 1 minus pf f comma 2 comma 21. So our p-value is 0.0467. Therefore, we reject the mean, or I'm sorry, reject the null, which assumed equal population means. So our decision at this point, we have reason to believe that at least one pair of population means is statistically significant. Okay, now we ran through this, by hand, and we're going to eventually go back to the whiteboard and complete the Anova table. But what I want to do now is I want to show you how I would carry this out using R. So first thing I found to be easiest is to put all of our data into one vector. So first, I'm going to place all of our data in one vector. And the way I'm going to do that is I'm just going to call this, whatever, V. And I'm going to oh guys, I can't even read my own writing. Okay. What did we call this thing? Let's see. Okay, we called it Anova, didn't we? So what I'll need to do here is CT as dot matrix Anova. And let's see, that's going to take CT as matrix. Okay, that should do it actually. So yeah, that's what we want. So notice that I have 22, 52, 16. It's really important to note the way that yeah, it's actually reading our data. So it's reading item 1, item 2, item 3, item 1, item 2, item 3. Right, yeah, because that's going to have a lot to do with the way I set this up. Okay, now what I'm going to want to do is I'm going to create a new variable. And let's call this one, well, I don't know, W will be fine. And what I want to do now is I want to sort of start distributing. Make sure this is going to work. Okay. Now I want K to be equal to number of treatments. And I want N to be equal to the sample size in each. Yeah, this is going to work. Okay. Now what I want to do is I want to create a vector of treatment factors that corresponds with what I created before. So I'm going to call this TM, and I'm going to run a general linear model for K. 1 n times K. Factor is going to be, what do we call that? V. No, factors for W. Let's see. Factor W, K, 1 row, n times K. Yeah, good. Now you can see what I did is I created by this, K is the number of times that I want each of these to occur. I want everything to occur one time, and of course I have n times K would be the number, kind of the stopping criterion, if you will, and then I want to set it according to the factor, item 1, item 2, item 3. So guess what I can do now is I can set my Anova to be W tilde. No, that's not right. It would be V tilde W. It's not working. Oh, I see what I did. Had a brain lapse. So I need I need V tilde Tm. So well, hold on now. I got V is my numbers. And then I have W, which is, no, it's not. Yeah, TM. So this is good. All right. So, well, guys, please accept my apologies on this one. Yeah, finally. All right. So we get sum of squares degrees of freedom for the model, for the residuals. All right, so to get a summary of our Anova, we get this. Now, I don't remember those being the answers we got before. I guess we can go back up and look at that. Our F value is off. And we have a difference in the degrees of freedom for the residuals. So I have U minus K, we have 6. Oh, I know what I did. Daggone it. Guys, look right back up here. I don't know why, but I multiplied 6. 6 times 3, I got 24. So that should clearly be 15. So I'm going to reset. Let's do the mean square. It'll keep everything. So if I go mean square to be the sum of squares, hold on, that's the between factor, right? Between or within, okay. So sum of squares within divided by our total sample size, which is 18 minus 3. I wonder if any of you caught that. Of course, you know, you can't tell me that, right? Because it's probably a week or so before you're ever going to listen to this. So we can let F be our mean squares between. So our F statistic is 2.54, which now lines up. And we could recalculate our p-value to be 1 minus pf 2.541095. One equals 2, 2 equals 15. Our p-value lines up, and you know what, guys? I think I even did that wrong. 2 and 21. Yep, sure did. Wow. All right. Well, it's corrected, and so this gives you an illustration of a very clumsy illustration. Good thing you guys have this on video where you can like stop and rewind and stuff. But everything's corrected, and of course everything's working out correctly. So p-value 0.112, whereas up here we had a p-value that was 0.046. So I have to change my interpretation. And since our p-value is greater than 0.05, we fail to reject the null, indicating there's no evidence against. All right, so there's not sufficient evidence to reject the claim that the population means are equal. And again, at the end of the day, we're not saying they're not equal. And it's something I try to get through to my undergrad students all the time. We have to take words like true and false and prove and disprove kind of out of our vocabulary when interpreting a p-value. The purpose of a testing hypothesis is to reject the null. And if our p-value is less than alpha, we reject. Doesn't mean that the null is false. Doesn't mean it's true. It's all about evidence from our sample. Really, which is it more supportive of? And I like to think of when we have a p-value less than alpha, then we have more support for the alternative hypothesis. If we have a p-value greater than or equal to alpha, then we have more support for the null, or at least we can't reject the null. So this is the end of this lecture, guys. I promise I'll try to make this make less mistakes. See, if this was in the classroom, I know that someone would have corrected me and said, Dr. Darbro, Doug, whatever you call me, 6 times 3 is not 24. So let's blame it on the dog, right? Okay.